Yeah, here we go with problems 7 through 9. Okay, so problem 7 is the first time we're actually going to officially tackle kind of a logarithmic differentiation problem. So here we go. We're actually specifically taking the log of sort of a complicated argument here. And so the first thing I'm going to do is I'm going to employ some of our rules of logarithms. So you want to remember that when it deals with logs, we have a couple little extra pieces. One is that the log, any kind of base of a over b is the log of a minus the log of b. We also want to remember that the log of a product, a times b, is the log of a plus the log of b. And our last rule was the log of any kind of base of a raised to the b is b times the log of a. Now those features are going to allow us to kind of rip this thing apart and turn it into something much easier. So instead of thinking about this the log of a product, I'm going to think about it using this rule right here, and I'm going to do the log of x plus 3 plus the log of 2x plus 9. So here we go. So in that first problem, the first thing I did is I just broke it apart. Now, keep in mind that is not actually any trig yet, or any calculus yet. We're literally just going to do simple analysis. So the derivative of y, of course, is y prime, or dy dx, and the derivative of any kind of natural log is 1 over u times u prime. So the derivative of this is 1 over what's inside times the derivative of what's inside, which in this case is 1. Over here, 1 over what's inside times the derivative of what's inside, which is, of course, 2. Now, the second question on number 7 really is sneaky because it is not explicitly a log differentiation problem, but this would be an absolutely atrocious problem to do. It's got product rule, it's got quotient rule, it's got chain rule. It's all doable, but man, I don't want to deal with it. So I'm going to take the log of both sides. And I'm going to do what I had you guys do in analysis last year, which is to expand that thing. Notice the 2 came in front because exponents become coefficients. We've got a product, so I mark it as a plus. And then there is a division, so I subtracted it. And instead of thinking about it as a root, I just thought it was a 1/2 power. Now, the derivative of this is going to be 1 over y prime. The derivative of that is 1 over what's inside. Again, the derivative of what's inside is 1. This one, actually, the derivative of what's inside is a 2. And this one, the derivative of what's inside is 6x. Now, this is all well and good. We've done something good. We've actually done the main body of the calculus here, but now we actually have to get y prime by itself. So what I need to do now to get rid of this 1 over y is multiply both sides by y. This is the part that a lot of people forget to do. So I just did all of that and I multiplied by y. Now, could we simplify that? Yes, but I didn't think it was worth the time. I just decided that I thought that was a reasonable place to end that atrocious little story. Now for question number 8, it's our first related rates problem. Water's flowing at a given rate into a cylinder with a radius of 12. Well, one of the nice things about that is, remember, in related rates problems, we're going to be watching specifically for when we actually have, just putting something away for a second, we're watching for any kind of constants, and the radius of that water tower is in fact a constant. So I started off with a nice picture. The volume of a cylinder is pi r squared h. Notice since the radius was a constant, it did not hurt for me to plug that in very, very quickly. And now dv dt is 145 pi dh dt. It doesn't matter how deep the water is at any moment, that no matter what, if the volume is changing at a constant rate, then the height is going to grow at a constant rate. It is not a pretty answer, but it's an answer nonetheless, and it was pretty easy. I know that sometimes we're looking for where to plug in that 5 feet, but if you've ever filled up a glass, it just comes up at a constant linear rate, so it doesn't matter what time you plugged it in. Okay, number 9 is the next one of those related rates problems, but this one is one that matters because if we're going to fill up any kind of a conical tank, Keep in mind, as the thing kind of goes up, the radius is going to grow as the height grows. And so as we go through that process, it says that the radius of the tank is 12 feet and the height is 7 feet. So we end up with these nice little similar triangles that actually occur because as the tank grows up, the radius and the height are going to be changing, but they're always going to be changing in such a way that the ratio of the radius to the height is 12 to 7. So I personally just did a quick cross multiplication. I figured out what the radius was in terms of the height, which allowed me to take the radius out and have everything in terms of the height, which is what I have right here. Now that's kind of an ugly looking answer, but the derivative of h cubed is 3h squared dh dt. Now keep in mind, in the problem, they told me that dv dt, they were pouring water in at 18 cubic feet per minute. And they also asked about the height specifically at 5, which is why I got rid of the radius, since they told me about the height. So in plugging those values in, notice that I did the derivative first before I plugged those things in. I was able to simplify this all the way down to get this expression right here. And with a little bit of more manipulation, at the time when the height was 5 feet, the rate of change of the height with respect to time was 49 over 200 pi feet per minute. It is important that you make some kind of a summary statement about it, because that's not to say that the DHDT is always this. It's only that at that particular moment when the height was 5 feet. Hey, I hope that that was, again, a helpful way to look over that. I'm kind of sorry I have to look over here a little bit, see the controls, and I'll be back with the next little chunk in a moment. Bye.